Okay, let's try example 5. This one's a little more complicated. This time we have things in the denominator, which means I have asymptotes and I have holes. So what I want you to do, try to pause the video, reduce the fraction, list any holes, plug them into the simplified one to get the points, and then look at your reduced one to get the asymptotes. Try that part on your own, similar to the examples we did on the first page of these notes, and see if you can do it. Ready, set, go. Okay, for our reduced form, we should have gotten this. Now, I didn't actually finish, and here's why. If I look at what canceled, I have an x that canceled, which would mean a hole at 0, and I have an x minus 1 that canceled, so that would be a hole at 1, because that's what makes this 0. But if I look at my reduced form, in the denominator I have an x, so that would be an asymptote at 0, and I have an x minus 3, which would be an asymptote at 3, because that's what makes that 0. But here's my problem. How is it that I could have a hole and an asymptote at the same place? That doesn't make sense, because an asymptote you will never ever touch. You'll get closer to, but never touch. That's not a hole. So when we talk, if we have anything competing, if we have an asymptote competing with a hole, asymptote wins. The asymptote means it'll get closer and closer, never touch, not a hole. So now I can finish this. I just need to plug 1 in. 1 minus 1 is 0. 1 plus 3 is 4 cubed. 1 in the denominator, and 1 minus 3 is negative 2 squared. If I simplify all that, I'm going to get 0. So there's my hole, there's my asymptotes, and now that I know all that, I can do my domain, negative infinity up to my first one. Looks like it's going to be 0. Then from 0 to my second one, oops, got that wrong, 0 to 1 to my hole, and then looks like 1 to 3 right there, and then from 3 to infinity. So I've got all my holes and asymptotes included in my domain. Okay, next I want you to pause the video, try the x-intercepts and the y-intercepts. Remember, x is when y equals 0. Y is when x equals 0. Try that. Ready, set, go. Okay, real quick, I want to take a second and explain. Whenever we had a rational function, up to this point we said x-intercepts were setting the numerator equal to 0, asymptotes were setting the denominator equal to 0. I want to go through and explain why x-intercepts are just the numerator. So x-intercept is when you set y equal to 0. So here's my equation in reduced form, and I set it equal to 0. Now, first step if I wanted to solve this is I would multiply both sides by this numerator to get rid of it. So then these cancel. I multiply this side by the denominator, so then I can get rid of the denominator. Makes it a lot simpler. Now notice, because I'm setting it equal to 0, because that's what I do for an x-intercept, your denominator will always just go away, because it's multiplying by 0. That's why we say we only set the numerator equal to 0, because the denominator, when I solve this, is going to be multiplied by 0, go away. Now that I have this, I would set each one equal to 0. So I have x minus 1 equals 0, and x plus 3 cubed equals 0. So I can cube root that, so then those just go away. And then I have, so x is going to be 1. This is an intercept, so I write it as a point, and negative 3, write it as a point. Now for the y-intercept, I plug 0 in for x, So then when I went to simplify this, I'm noticing, hey, I'm dividing by 0, which means I do not have a y-intercept. Okay, we got both of those done. Last thing to do is the end behavior. So what I want you to do, go through this equation, think about what numbers would become inconsequential, unimportant, as I go to infinity, and then simplify it to see what your end behavior would be. So pause the video, try doing that part on your own, come back to see if you're right. Okay, let's look at our end behavior. So here's my equation right here. The -1, the +3, and the -3 all become unimportant when we're talking about infinity, so they go away. So I get x times x cubed and x times x squared, so I get x to the 4th over x cubed, which simplifies to x. Now, this x is telling you what the ends of the graph are doing, how it behaves at the end points. That's why we call it end behavior. So if I think about the graph of y equals x, I know it's this diagonal line. So if I look at the ends of this diagonal line, it's telling me what my limits are. So the limit as x goes to infinity, that's the right hand. That one's going up to infinity. Then I say as x goes to negative infinity, that's the left hand. Well, the left is going down to negative infinity. That's how you figure out your end behaviors. Now let's go through and graph all of this. So vertical asymptotes are always graphed as vertical lines, vertical dotted lines specifically. So I have one there at 0 and one at 3. Then I have asymptotes, I have a hole, that's what I meant to say, at 1, 0. So I have a hole right there. Then I have x-intercepts at 1, 0 and -3, 0. Hey, wait a minute. How can I have a hole and an intercept at the same place? That doesn't make any sense. In this case, the hole would win. That would not be an x-intercept. The hole wins. So I have a hole at 1, 0 and x-intercept at -3, 0. No y-intercept, and my end behavior to the right is going to go up to infinity, and to the left is going to go down to negative infinity. So now I need to start graphing this. So this first one, if I know I need to go down to negative infinity, then I know I need to head to that point. I can double check that with my sine line. On my sine line, I'm going to have -3. That's a place where it could change from positive to negative. I'm going to have my asymptote at 0. I'm going to have this hole at 1, because that hole is on the x-axis, so that could be a place where it bounces off the hole or goes through the hole. And I'm going to have 3. That's a place where it could change from positive to negative or vice versa. So I'm going to start over here with -3. I want you to pause the video, pick a number left of -3, say -4, plug it into our reduced version, and see if it's going to be positive or negative. You should get negative, like we've already seen in the graph. Ready, set, go. Okay, so I plugged in -4. -4 minus 1 is a negative. -4 plus 3 is a negative, and cubed stays a negative. -4 in for x is a negative. -4 minus 3 is a negative, but then I square it, and it's a positive. So I simplify the top. A negative times a negative is a positive. Simplify the bottom. A negative times a positive is a negative. And then simplify division. Positive divided by a negative gives me a negative. So that fits with my graph so far. Now, I want you to practice sign lines. They're going to be really important in calculus. So what I want you to do is pause the video, pick a number between -3 and 0, test it, pick a number between 0 and 1, test it, pick a number between 1 and 3, test it, and then pick a number right of 3 and test it so that you can practice those sign line skills because they will come back. So pause the video, try that out. Okay, here's how your sign line should have turned out. If you need to pause the video so you can look at this a little more closely and see which sign you missed, you can double check, go back and double check that. Go ahead and do that now. But this is what we should get. So this tells us at -3, I'm going from the bottom half to the top half. So this graph is going to go through that x-intercept, not bounce off of it. Now, this means I'm getting to an asymptote here. I cannot ever cross an asymptote. So that means this is just going to go up forever and have a line. Now, from 0 to 1, that's a negative. I cannot cross that asymptote, so I'm going to go along it and then go up to my hole. From 1 to 3, it's positive, so that means I'm going to cross through this hole from bottom half to top half. Come to my asymptote. I cannot cross that asymptote, so I'm just going to run alongside it. This last one needs to stay positive. So I cannot go in the bottom half. I have to stay in the top half. So I know I'm going to run alongside my asymptote. And I also know I have to match my end behavior. So this part of the graph is going to make this funky V-U-shaped thing. Because I can't go in the bottom half. I can't cross my asymptote. So I have to follow along it. And I have to end up here at my end behavior. So that's the sketch of this graph. Now, right now, you don't need to worry how low this has to go. We'll talk about that at a later date. Now, one last thing I want to talk about for this problem, this example. If I look at my reduced fraction, it's going to tell me if these cross or bounce. So if I look at -3, this is the part that gave me that -3. If I look at the exponent, that is an odd exponent, which means it's going to cross through. So I knew right there this one would have to cross and then follow. Now if I look at this asymptote at 0, here's that one. It has a silent 1, which is also an odd exponent, which means, if you remember from our limits at infinity, I have two options. Here's my asymptote. I could go up and then down, or I could go down and then up. That's what odd means for your asymptotes. Well, I knew that this one was going to have to cross through, so it was going to go up. So then from there I could infer that this one would have to go down, the opposite one, because it's odd. Then I come to this 1 right here. That came from this part of the graph. Well, it also has a silent 1, which is odd. So that tells me I would cross through this x-intercept because the exponent is odd. Now this last part at 3. That 3 came from this part. This is an even exponent, and it's an asymptote. So if you remember from our lesson on asymptotes, that is two options. So here's my asymptote. It could either both go up or both go down. That's what an even asymptote means. And since I knew that this one had to cross through the 1, so it had to go up, then I would know that this one would also need to be up because it's even, so they're both going to go the same direction. So those are two completely separate different methods. You can do the sign line, always works to know what direction, top half or bottom half, positive or negative. Or you can use your exponents to know if you should cross through, or bounce off, or for your asymptotes, they're going to go different directions or same directions. So there's that graph. In the next example, we'll do number 6.